All right. Good noon, everyone. Now, let me get some more light in here. Good noon. Only one more week of classes now. So that's exciting, hopefully, maybe. Um, so, reminder that next Wednesday, the 22nd, is going to be our final. And today I'm going to go ahead and check on if we have to have that final in the exact time frame that they gave us. So, I'll send out some emails. And then this Wednesday, I will get the final details to you all on what the exam will look like, along with the time frames when it'll be, and I'll post all those kind of details in writing, and I'll also make edits to the final exam assignment on web courses so it'll reflect all of that as well. So today we're going to be continuing with optics. So last class we didn't get through as much as I initially thought, but that's perfectly fine. We still have lots of time. All right, there we go. Things are moving. So last time we started with optics, and we started talking about how light is actually these electric fields and magnetic fields which oscillate, and that these waves have characteristics. They have an amplitude, they have a wavelength, based on their wavelength, and based on how fast they're going, which in vacuum is the speed of light. You get a frequency, which says how quickly these waves are oscillating up and down, whether they're going up and down really, really quickly, or whether it is something that is occurring over a longer time span. We looked at a bunch of different wavelengths, from the radio band to the gamma ray, and then we saw that the visible is very small. So when we think of light, we often think of the visible spectrum, but in reality, there is a vast electromagnetic spectrum, where the visible spectrum is just a tiny piece of that. Okay, and then talked about a literal microwave that you use to heat up your food, how that works. I gave you all the quicker question here. We started talking about reflection and that things bounce off with the same angle that they come in at. And so for a flat surface, that's really simple. For a bumpy surface, you have to find the tangent line to that surface, or aka you have to find the normal area vector for each thing. And we talked about some unique cases of that, some unique engineering kind of thoughts with that. Okay, so that leads us, so that's a quick recap of what we did last time. And today we are going to be talking about light traveling from one medium to another. And when I say medium, that literally means anything that light can travel through. So air, water, oil, anything that's kind of, I'm going to use the word transparent. And what's interesting is the transparency, whether light can go through things, will actually depend upon the wavelength and the frequency. And we're not going to get into that, but I just mentioned that as, for instance, some things may be transparent to, for instance, infrared, whereas things aren't transparent to visible. So an easy example of that is infrared. If someone's using an infrared camera, they will actually be able to see a person who is emanating that heat through things that you couldn't see through visibly. So for instance, maybe if there's a thin sheet or even clothing, you could see through visible clothing. Even though visible light doesn't go through that, you can see the outline of the person underneath it. Same, X-rays are another clear example. I mean, that's probably even an easier one. You can't literally see your bones, but X-rays are able to go through your skin. They aren't able to really go through your bones because they're denser. So all that to say, different wavelengths go through different mediums, and so this isn't limited necessarily to the visible spectrum, but I will say that all our examples will be pretty much in the visible spectrum, just for the sake of simplicity. Okay, so all that to say, light travels through things. It goes from one medium to another. The big thing here is that light travels at different speeds, and this has a very specific consequence, which is that as it's traveling, it's fine. As light is traveling, so this is one medium to another medium, you see here that as the light hits, it actually bends. And this is something you've seen in the real world. This is something you've seen whenever you've interacted with, whenever you looked in water, and if you tried to grab something in water and your hand went for it, it was probably slightly off. of where it looked like it was. If you thought it was straight in front of you, it's actually probably down a bit. And the idea behind this is, imagine each of these is, and that's actually the other link I sent you. Imagine they're like a marching band, and this is a column of people walking together. Well, when they hit this, imagine that this is a rougher surface or something like that where they have to go slower. So they're going faster in this light blue region and slower in the dark green region to the right. And so once they hit it, they're going slower. So these people immediately start going slower, but these are still going just as fast. So these are going slower, but they keep these straight lines, so slow. And so you need to keep this like connected. And so you can see here, once it hits it, it starts going slower, but the consequence is it's traveled farther by the time it starts going slower. So you see here, this top part's traveled much farther than this one. So if we look at the bottom part of the wave, let's just track one of them. You see here, the bottom part is all the way back here because it got slowed down much sooner. Whereas let's look at another one. The top part keeps moving fast and moves farther ahead. The result is that each of these waves end up getting bent because the ones above it are traveling faster, go a farther distance. So by the time they hit the slower medium and start going the same speed, they're farther to the right of it. And as each point does that, you get this curve because each point will have traveled farther, and by the time it hits it then will bend. So this is the general idea of why light bends when it goes from a lighter medium to a denser medium. Light's going to travel slower in denser mediums. It's going to travel faster in less dense mediums. And the fastest it's going to travel in vacuum, which is the least dense medium there is because it's nothing. It's literal nothing. And density is defined by how closely packed things are together. If you have nothing, then that's as least dense as you can get. So this is the concept. This is the idea. Things, and if you go the other way, so if we could reverse this, which I can't, but if you did, you would see that as they're going, it would then bend from this angle to going flat. So it's a little weird, and I recommend this YouTube video. I think does a really good job of explaining it. So if you want some more explanation, please watch this YouTube video that I provided here. But that's certainly not necessary. Oh, that's a good. So Mason said, so light would not bend if it was perpendicular when entering the medium. So perpendicular meaning if it was straight on, correct. If this medium was actually straight up and down, so I even draw that here. If we had a interface, and we'll actually see this with the math later on. If you had an interface that's like this and light is going into it, the light is going to keep going the same exact direction. You are completely correct. It will not bend at all. Won't bend if hitting interface head on. I'm going to say head on, and you can see that here. So this is interface 1, interface 2. Who cares if it's less dense or more dense? As long as this medium over here is also transparent, it's going to go straight through. It's not going to bend at all. So yeah, that's a really good question. Okay, so this leads us to this idea of index of refraction. So we have to talk about this idea before we kind of can get to the math. The index of refraction is the ratio of the speed of light in vacuum to the speed of light in some material. There's no units for this because the speed of light has meters per second. Velocity has meters per second, so they end up canceling each other out and you get no units. The idea here is that, as we said, light travels slower in everything other, so it travels the fastest in vacuum. Anything else is going to travel slower. So this N basically just gives us how much slower does it travel. So N is always going to be bigger than 1 because V is always less than C. So any medium other than vacuum, so light, the maximum it can travel is C. So if it's going through anything else, it's going to travel slower than that. So you put a bigger number over a smaller number, you get a big number bigger than 1. And this just tells us how much slower it is. Let's just hypothetically make up an example. Say V is equal to 0.5 C in some medium. So in some random medium, I don't know what this medium is, I'm making it up. In some random medium, it's 0.5 c. That would mean that n equals c over v equals c over 0.5 c equals 2. So if you had an n of 2, let's go backwards with this. If you have an n of 2, that means that light travels half as fast. It travels half the speed of light in it. If you have an n of 3, that means it travels a third the speed of light, so on and so forth. So this is just a useful kind of ratio to just give us a sense of, okay, how does light behave in this? How much slower, or, well, I say slow, how much slower does it travel in this compared to vacuum? Vacuum's always our standard because that's the maximum. Okay. We're going to be using this index of refraction. And so let me actually give you a bunch of random numbers for this. So I say random numbers. These are values for various mediums. What's interesting is you're going to notice here I give you temperature and pressure because these will change at varying temperatures and pressure. I'll go ahead and tell you on a test, I'm just going to give you what N is. I'm not going to say, oh, pick this thing, pick this gas at this temperature, at this pressure, and make you Google it. No. I'll just give you the value of N, or I'll be asking you to find the value of N. So you're not going to need to worry about looking things up like this. I'll just give this to you. Now you can see here we get different values for each one. And again, the temperature and pressure matters because each of these, let's increase the temperature. What's going to happen if I increase the temperature? Well, they're going to be moving faster, and that's going to affect how light's going to travel through. It's going to make it probably more dense. Same thing with if I increase the pressure, I increase usually the density of the medium. Light's going to scatter off of more things. It's going to go slower. And you see here, as we start at air pretty much all very close to 1. Air does not slow down light really much at all. It does slow it down very little. I mean, we can do the calculations and see how much, but it's minuscule. It's like nothing. As you start to get to liquids, more denser mediums, you start to get to some more significant values. We see water. We're going to be using the water value very often because that's just an easy example. Everyone's familiar with water. But you can see here different liquids at room temperature all have different index of refraction. And then if you see you start getting to when you start getting to solids, you get even different ones, and we actually see that diamond has a very high index of refraction, which means that it's and this makes sense, diamond's very dense. It's very hard. The crystalline structure is very tightly packed, and so it's going to be harder for light to travel through it. It's going to travel slower. Where we see regular glass, it's much less, and so on and so forth. Just a bunch of different values here, just to kind of see that, okay, light travels differently in different mediums, and as you get to denser mediums, you get slower velocities, aka you get higher index of refraction because light's traveling slower. Okay, so that's just index of refraction, just light's going to travel at different speeds in different mediums. And we're going to use that concept. Remember, the way the light bends has to do with the light moves slower. So that's why we're talking about this. Well, if we can figure out there is going to be some relationship between how fast light travels and how much it bends between two interfaces. And that's where we get to Snell's law, which is this super nice equation. It's really amazing how simple of an equation it is for determining how light bends when it goes from one medium to another medium. That can go from a lighter medium to a less dense medium to a more dense medium, or from a more dense medium to a less dense medium. You can see here we're going from, we'll just call this maybe air to water because that's what it looks like. So this is air and this is H2O. This is air and this is H2O. And you can see here when I go from a lighter medium to a denser medium, the light bends towards the normal. The normal, remember, hopefully familiar with the normal at this point, that's the area vector on the surface. So we're going to make certain you're comfortable drawing these area vectors, because this is going to determine how the light's going to bend. Our angle, so our equation is N1 sine theta 1 equals N2 sine theta 2. And what this means, so theta 1 and theta 2 are here. Theta 1 is the incident angle. Incident angle, that just means, if we look at our picture, it's the angle. So the light comes in, it's the angle between the light ray and that normal vector. So draw the normal vector, draw your light ray hitting the surface. It's the angle between those two. And then we call theta 2 here the exit angle. It is the angle now that it's passed into the new medium. It's between the new ray that we get and the area vector on the other side. Each of these has an area vector. So it's the angle between that area vector and the new medium and the new light ray. Okay, and then N1 and N2 this is just going to be the index of refraction for whatever it's coming from. And this is the index of refraction N2. Oh, and actually, let me fix these. This one would be N1, N2, and let's just even call this theta 2, theta 1. I don't like how these are labeled. I did not make this graphic, just to keep it consistent. Usually it's good to keep theta 1 as the incident angle, and theta 2 is the exit one. So in the picture here, B, incident now is coming from the denser medium, so I just relabeled those accordingly. And then whatever medium you're in, you would just, so if this was a problem, this is a problem you were asked to solve, you would just say, for instance, I asked, okay, I'm going from air to water, and I come in with 30 degrees. What is my exit angle? Well, you would plug in N1 of your coming, so N1 is where you're coming from, so you just plug that in for air. You'd plug in 30 degrees here. You'd plug in N2 for water, because I told you it's water. You'd be able to plug that in, and then you would just solve for this. Don't worry, I'll actually do a real example with this, but just quickly kind of say what you would do. All right. And then this is the general idea. This is why you see weird things when you look at two different mediums. Light comes in. Each of your eyes actually sees that corner. So your left eye is going to kind of see the left side. Your right eye is going to see the right side. Even with just one eye is actually going to see both sides. So you don't even need two eyes for this. And you end up seeing three fish here because of how this light bends. The fish is actually here, but the way the light bends makes it look like it's in these other places. Because we imagine that this light ray, if it traveled straight, you would end up seeing that fish. So your mind's like, oh, there must be a fish here on the left and here on the right, when actuality it's dead center. Anyway, I'll come back to this, spend a bit more time talking about this, but we'll go ahead and take our 2-minute break. So we'll come back at like 11:51. And if you have any questions about this stuff, let me know. You can take this time to watch the video if you want. Just go through these slides, maybe think through some of this stuff, and just kind of wrap your head around this idea of light bending more than anything. And then when we come back, we'll do some practice with these index of refraction. So 11:51. And I'll do the usual. Oh, where is he? There he is. That's him in his wonderful dog bed that he has in the corner of our room. Let's see. Yeah, that looks decent enough. He just stared at me. Well, fortunately, I can't stay there because he's too low to the ground for it to stay. Okay. So resuming with our light bending. So this is an example problem. This asks, what is the angle that light would enter water from air if it entered at a 60-degree angle to the normal? The first step when solving these problems is the same step I tell you all pretty much every time. Draw a picture. So we draw our interface. We'll call this air up here. We'll call this H2O down here. We're going to draw our light coming in like this. We see, and we have to make certain, so light would enter water from air. So make certain you draw the arrow going from the right thing to the right thing. This is not going from water to air. It's going from air to water because it's entering water. And then it says it enters at a 60-degree angle to the normal. There's our normal. There's our 60-degree angle. And then it's going to hit the water. And remember, we always know it's going to bend towards, if it goes from a lighter medium to a denser medium, bends towards the normal. And the question is asking, what is this angle? So at this point, you're just going to set up, and this has an N1, and this has an N2. We'll even put these values here. Always good to kind of list these things where they're at. I'll go ahead and tell you pretty much for every problem, you can just use n equals 1 for air. You can see that this 0.0003 is going to make almost, you can go ahead and plug it in both ways. Try it with the 1.0003 and try it with the 1.00. And you're going to see your answer is not really going to change at all. So very often we actually consider air to just be approximately 1. And even interestingly, when I say air is technically made up of carbon dioxide, hydrogen, oxygen, nitrogen. Air is kind of a combination of all of these. So that's another little fun point. But yeah, so you're just going to use your N1 sine theta 1 equals N2 sine theta 2. We're looking for the exit angle. So there you go. Kind of set it up all for you. But that's the gist of it. And this is pretty much how most of the problems are going to look like. One of the things I could say is I say it enters at some angle, it exits at some angle, and I tell you what it's coming from, and I say, oh, what's the index of refraction for the new material? And this is actually an interesting thing because you could actually use this as a way to characterize a material. I don't know if they actually do this, but you could see that there's a practical application here. I mean, there's a ton of practical applications here. You need to know how light's going to behave as it bounces through things. Because if you're trying to shoot a laser, for instance, and you want it to go to a specific spot and you have it passing through different mediums, you need to know how it's going to bend. So that's one easy way. But you could see that if I shot a laser through from one medium, just say from air into a medium, and I see the new medium, it bends a certain way, you could use that to characterize, okay, we could find the index of refraction for that, and that may actually help you identify what the material is that you're shooting it into. Again, I don't know if they actually do this. It could be that the index of refractions are actually very similar for certain materials, so you could encounter some challenges identifying things because of that. Again, I don't know too much, but just thinking off the top of my head, that's a really easy engineering application that you could use this for. Another one is if you were trying to design any kind of, just say, the silly one is you're trying to shoot a fish in water. Maybe you're not trying to shoot a fish in water, but if you were, or you're trying to just hit something into water and make it have to go to a specific spot, light-wise, you're going to need to know this. I don't know. Again, that kind of falls into the same thing. Okay, all that to say, the next conceptual question is going to be, what is the maximum angle theta can reach, and what effect does this have? Okay, so this is kind of a weirdly worded question. But what I want you to, let's go ahead and look at our picture. Here's light coming in, and it's going to bounce off somewhere. Let's just say it's going to a lighter medium, and it bends a little bit towards it. This angle has limitations. You can only go, so what's our extremes? Well, our extreme is either light goes straight down into it, at which case the angle is 0. Theta equals 0 if it's going straight down. The other extreme is that light could be coming in at a 90-degree angle and so theta equals 90. That's the extent of it. Theta can be between 0 and 90. There is no other values based on this geometry that we can potentially get. And so this has some interesting consequences. Because, let's go ahead and think of our equation here. Okay, we have our sine of theta. So sine of theta can either be less than or equal to 1 or less than or equal to 0. That is the extent that sine of theta can be. It cannot be bigger than 1. It cannot be less than 0. And so this results in some constraints. Because let's just make up the example of water. So, going from air to water. So we have air to water. I'll write that down. Air to H2O. So in that case, N1 is going to be 1. And I have my sine of theta 1. Sine of theta incident equals 1.33 sine of theta, I'll just call it F. Well, let's do E to keep it with that incident and exiting. Okay. So looking at this, you may be like, okay, this all looks fine. No problems here. But what if your theta, so what if it's coming in from here? Let's go ahead. So let's instead kind of flip well, let's just keep it like this. So if I do 1.33 divided by 1.00, so I divided this one over, we get 1.33. We get that equals sine of theta incident over sine of theta exiting. Okay? This value is bigger than 1. So this value is bigger than 1, and so that's fine, because theta incident can be, we can say that can go from anywhere from 0 to 1, and then theta exit can be anywhere less than that. No problem. But things get a little tricky when I have the other way around. Because now this number is less than 1. And so if this value, ends up being less than this value, there's not much we can do. Let me go ahead and go to the next example because I think that's going to clarify it. So this is the clicker question I'm going to give you all, so I'll go ahead and set it up for you. So instead of light going into water, we're going the other way. Light is now leaving water, so it is coming in at this angle, some angle. And the question is, what is the incident angle at which the exiting angle equals 90 degrees? So here's my theta incident. We know this is still 1.33. We know up here it's 1.00. And the question is, when the exiting angle equals, and I'm going to use a different color for this. What happens when the exiting angle is 90 degrees? And we'll go ahead and just see, is this even possible? I'm going to leave the math for you all. I'll tell you it is possible. So let's just set up our equation. So we have N2 times sine theta incident equals N1 times sine theta exiting. So we go ahead and plug in our values. 1.33 times sine of theta incident, this is what we're solving for, equals 1.00 times sine of 90. Well, sine of 90 is going to be 1. So basically it just equals 1. And here's where you get your kind of interesting result. We have sine of theta incident equals 1.00 divided by 1.33. Which is fine. No problem. Sine of theta incident can totally be that. But here's the interesting thing. And so I'm going to leave you all to solve what that value is. At some point, let's just go ahead and say I increased my incident angle. So you're going to find this value. You're going to see what it is, and this is the value at which point this one goes exactly to the right. This is the largest that this right side can get. This right side, 1.00 times sine of theta, cannot get any bigger than this value because N1 is always 1. It's air. Every single time it's going to be 1. That does not change. We could change the medium, but for our case, it's air. It's always going to be air. The only thing we can change is that exit angle. Well, no matter what value we make the exit angle, you can't make sine of theta be bigger than 1. That is the maximum value can be is 1. So that means the maximum value this right side can be is 1 for this specific problem. So if I increase my incident angle, that's going to increase the left side, but that's just not, I can't increase the right side to balance it out. And so this is where the critical angle comes from. This is where a very special case, when you're going from a denser medium to a lighter medium, as your light ray gets closer and closer to this incident angle, as this light ray bends farther and farther away from the normal, your reflected ray is going to, so let's just go ahead and draw another one here. It's going to move farther and farther. The exit angle is going to move closer and closer to that 90 degrees. At some point, you're going to reach that 90 degrees. And if I increase this angle any little bit more, it's not going to exit the material at all. This is called total internal reflection. And one thing I want to clarify here is when you're going from a denser medium to a lighter medium, not only does some of it actually go through it, and actually go, so from example, water to air, but some of it will reflect. So this is, for example, if you're looking up, say you're in water and you're looking up at the surface of the water, you will both see some reflection, but you'll also see the sky a little bit. You'll see both at the same time. But at some point, if you look at it with a very specific angle, well, if you look at it at an angle or in any angle greater than that, say you're swimming and you're here and you're looking at this exact point and you start moving up, at some point you'll no longer see the sky. The light will only reflect. You will not get, light coming from it will not exit the medium. And this is called total internal reflection. That critical angle is the one that you will calculate for at least the water-air interface. You're going to calculate that one in the last problem. And I already set up everything for you. And any angle bigger than this, any angle where my light, let's just draw an example one. If my light is coming in at an angle, which is, you can see here, this angle is bigger than the critical angle, it's going to all reflect. And it's going to reflect at the same angle it hits the normal with. So we use our rules for reflection there. So this is a very interesting phenomenon. This is very useful. This is the idea behind fiber optic cables. You've probably heard of this before. Fiber optic cables work by light is actually traveling through them. So instead of most cables, which use what we've talked about, which is electrons moving, fiber optic cables actually use light. And you want to keep the light in the cable, because if the light left the cable, then you lost your signal and it's not going to where you want it to. So fiber optic cables work by having glass and then some thicker medium on the outside. So pretty much usually the inside's glass of some sort. The outer is some denser medium where the light will hit it, and actually, instead of transmitting into that thicker medium, the angle it hits at, no matter where it's going from, it's always going to hit it with an angle bigger than the critical angle. And so you get this internal reflection. And so the light's just bouncing all the way through that cable, even when you have bends in the cable. It doesn't matter. It's going to keep bouncing, and it's going to eventually reach the end. One thing with these is you can't, for one, if you just tried to bend them too tightly, it's glass, so it's just going to shatter. So you don't actually get these, because you may be like, oh, but what if this thing was really, really bent? Well, if it's really, really bent, you're actually going to break the cable just due to how the materials it's made of. So you don't run into problems with ever getting a critical angle less than that because of that restriction. Okay, so that concludes it for today. So we've now talked about, this is called refraction. So we talked about reflection. Now we've talked about refraction. Refraction is just the bending of light. We talked about the mechanism, how that bending works, that it goes from a faster to a slower or slower to faster, and that results in it bending, the equation for it, and this internal reflection. Complete, where's the slide for that? Total internal reflection. And so that's two of the big topics covered. Next class, we're going to start talking about lenses. Lenses are ways for us to take light and either focus it or disperse it. And each of these has different applications that we'll talk about next time, and we'll talk about the math behind them. But that will be the last thing that we'll be covering in the entire class. We will have the review days, but this is the last new content that we'll be covering. So look forward to that. All right. You all have a good rest of the day. I will go ahead and make the video for the clicker questions from last time. And if you have any questions on any of this or anything else, as always, please email me, or I will see you in my office hours if you want to join me for those as well. All right. Have a good rest of the day.